In the previous videos we saw how to map reads to a reference. With those mapped reads we can now start to look for mutations at certain positions. The complete workflow for variant discovery looks like this. We started with the raw input, the FASTQ files, and went through a number of steps to end up with map reads in a BEM file. In the next steps we have to convert this into a position-based pileup file, which is a file that lists all identified bases per position. Next we have to identify the differences from that list and create a VCF file. Schematically it looks like this. We have a reference and have mapped reads to that reference. We then look at each position separately and check if the base in the read at that position is the same as the reference or not. In this case we have one location where all the reads have a different base compared to the reference. Normally you would have to go through all the steps individually, but we provide two pipelines in Galaxy that perform all steps for you. The two pipelines are based on the tools JTK and SAMtools. The JTK pipeline is created following the JTK best practices, but is much longer than the SAMtools one and therefore also takes longer to complete. We will start the demonstration using the SAMtools pipeline. You can find this pipeline in NGS variant analysis and then the tool SAMtools variant calling. So there's only two things that you need to provide. The first one is a reference sequence. So here we have the Neisseria meningitis reference that we also used in the previous videos, and a BOM file. And in this case we have the BOM file created with BWA mem on this reference sequence. All the other options can remain as is. So we just click on execute and the pipeline will start running. So this will take a few minutes. Once it's ready, I'll get back to you. So the analysis has finished now, and we can have a look at the output data by clicking on the eye icon. And this will open the VCF file. VCF stands for variant call format, and all the positions that you find in the VCF file are the ones that are different from the reference. The positions that are not different from the reference are not found in this file unless specifically requested in the options. The lines in the VCF file that start with two hash signs are all part of the header. Here you can find a lot of information that can be used to interpret the rest of the file. The next line with the single hash sign shows the column names for the data below. All the other lines are the actual data. In each line of the data we can find the chromosome name, the position of the variant, an optional ID, the reference at that position, the observed alternate at the position, the quality, whether or not it passed the filter, an info field where you can find the meaning of the abbreviations in the header, and a format field that explains what the numbers mean in the following columns, and of which you can also find the meaning of the abbreviations in the header. One important value in the last column is the genotype. The 0 means reference and a 1 or 2 means alternate. So 00 would be homozygous reference, but we do not find this in our file as these positions are not mentioned. A 10 means that it is heterozygous, and a 11 means that it is homozygous alternate. A 12 finally means that it is heterozygous, but that both bases are different from the reference. This is of course only when we are talking about a diploid organism, as you would only find 11 in case of a haploid organism. This is because all the heterozygous snips that are found during the analysis are filtered out by the pipeline, as they can be considered to be of low quality. If you want to know how many variants are found in the sample, you can just expand the SAMtools output here and you will see that there are 37,195 lines and 34 comments. As each line in the VCF file represents a variant, you can conclude that there are 37,195 variants found in this sample. Now, I said before, we can also do the same thing with GTK. So if we go to the tool panel here and we click on GTK variant calling, here we have to give a little bit more input. So the reference we also have to give. We had a paired end experiment. So the forward reads are the trimmed reads here, the R1 paired, and the reverse reads are the R2 paired. The BOM file is the same one that we use for the SAMtools. And we can leave all the other options as is and just click execute. Now, as said before, this one will run much longer. So once it has finished, I'll get back to you. So GTK has finished running now. And we see that this time we get two output files by default. The first one is the VCF again. If we open it, we see that we have 36,845 variants. You'll also notice that this is not the exact same number as we had for some tools. So every pipeline will give a different number of identified variants. Another output file that we get is a consensus sequence. So based on the variants that are detected, the consensus sequence can be created. And this is actually just based on the reference sequence that you gave, but with the detected variants filled in on those positions. Now the GTK pipeline is, as it says, a complete pipeline. You could also do this entire pipeline yourself by just connecting all the different tools that are used in this pipeline and get to the same output. Now the variants that are found in the VCF are all variants that were found by either SumTools or GTK. But if we look at this example, where the same variant was identified in both cases, we see that on the left it was identified in 1 out of 2 reads, while on the right it was identified in 1 out of 7 reads. So it's much more likely that the variant on the right is a sequencing error, while the variant on the left might be an actual variant. This is of course assuming that there was only one species present in our sample. Once you might have another minority species in your sample, this straightforward reasoning no longer applies. If you want to remove spurious snips, we can set thresholds on a minimal read depth, minimal snip quality, a minimal distance between the snips, or a minimum mapping quality. These are for now the ones that we provide in our tool to filter snips. If you would like something else added, please contact us and we will see if it's possible to add this filter to our pipeline. So to do the actual filtering, we can go to the tools here. We still are in NGS variant analysis, but you will see here the variant filtering tool. So as you see, we can filter on a minimal depth, quality, distance, or z-score. So the only thing that we need to provide is our VCF file. I'm going to take the SumTools one, because as it's noted down here, that the tool is developed specifically for VCF files generated with SumTools or BCF tools, and it might not work with GTK VCF files. So we just take our SumTools file, going to leave all the other options as is for now, and just click execute. So this is running now, and I'll get back once it has finished. It has finished running, and we get two new output files. So the first one here is just another VCF file. So if we look at it by clicking on the eye icon, we will see that's identical format as the one before, but now we have much less variance compared to the ones before. So now we have almost 14,000, while it used to be 36,000. So it's reduced by a lot. We can also look here at the filtering stats. So you will see how many variants were in the input and how many variants were in the output of each filtering step. So you can see which variant was removed by which filter. And with this we have arrived at the end of this video.